Good morning, Astronomy 1010. Welcome to the second part of Lecture 3, where we're going to continue learning about the history of astronomy. We've got a homework from Chapter 3 today, which is fun and easy. All around, fun and easy day. Let's see what you guys remember to start off. Can anyone remember Aristotle's argument for why the Earth must be the center of the cosmos? Aristotle had a profoundly logical argument about why Earth should not be in motion, but Earth should be the center of the cosmos. It would be good for you guys to remember that. Jonathan, are you doing this?
Yes, I'm saying because the Earth was the center and then all the other planets rotated around it. And then the angle at which we see it, for like even stars would be
the angle at which we see what? Hold on, John. The angle at which we see what? What is it?
What is that word now?
There is a fancy word for this. Look at your notes. It's okay to use to cheat and look at your notes. That's what we do here, right?
Right.
See, why do I need to ask you this? My whole discussion today depends upon you remembering this. The whole history of astronomy depends upon Aristotle's argument for why the Earth could not orbit the sun. You guys may not realize this, but maybe thousands of years before Copernicus ever walked the Earth, there was a famous Greek Aristarchus of Samos who had done this really clever thing in like 300 before Common Era. He had observed the moon at two different phases. Let's see if they have a diagram of this here. I guess this is one of his ancient works which survives here. He had calculated the relative distances to the sun and to the moon based on two different angles in the moon's orbit. I think he observed the moon at like first quarter phase, and then he observed
Parallax?
Oh, someone said it.
Parallax.
Parallax. Okay. So tell me what's up with parallax, Jonathan.
Argued the shift in positions of stars due to moving Earth. So the no shift in position of stars. All right. So the angle at which we see them, it didn't change. They were in the same place.
Right. In other words, if you went out and looked at your favorite constellation, which could be, wait, let me go over to Big Me here. If you went and looked at your favorite constellation, Orion has a belt and some feet and like three and some shoulders, right? The relative positions of those stars, argues Aristotle. Sorry, I've got glare. Let me fix my glare. His argument was that when you look at your favorite constellation, like Orion, the relative relationships between the stars never seem to change. These three stars in the belt, and by the way, you guys should realize that when we see stars in the sky, we see them as angles. Remember that your outstretched finger subtends 1 degree. I would guess that there's probably a 5-degree angle or so between the end stars on Orion's belt. And Aristotle's point is these stars are 5 degrees apart on the sky, and they have never changed their relative orientation. And yet Aristotle's argument is, if Earth is moving around the sun, so let's go back to that Greek geocentric universe for a second. This is helpful in case you missed Monday's lecture. You may not exactly understand what the hay is going on here today. In the Greek cosmos, which was a geocentric cosmos, see slide 39, function F5 39. Earth was the center of the cosmos. The planets had mostly the order that they do today, with the sun being between Venus and Mars. And then outside the orbit of Saturn was a final sphere, a fixed sphere of stars. The sphere rotated around Earth. That's how the nighttime sky worked for them. But the stars were all fixed in their geometric relationships to each other. As I was mentioning before you guys chimed in with the buzzword parallax, there were philosophers in ancient Greece who proposed that Earth might not be the center of the cosmos. And this Aristarchus fellow, he had calculated the relative distances to the sun and moon based on two different phases of the moon in orbit. Basically, he had performed this calculation where he figured out that the sun was 400 times farther away than Earth. So Aristarchus says, listen, guys, both the moon and the sun have an angular size of, take it away, class, show me what you know, impress me with your knowledge. What is the angular size of the sun and moon?
Half a degree.
1/2 degree. That's good. That's the kind of thing I want you to know about. If the angular size of the sun and moon are both 1/2 degree, what does it suggest, students, if Aristarchus computed that the sun is 400 times more distant than the moon? What would that imply about the sun and the moon?
The sun is way bigger.
Yeah, like 400 times bigger. And Aristarchus said, don't you think it's weird that the sun is 400 times bigger than the moon, but the sun is orbiting around us? That's kind of whack. Maybe the sun should, and he actually proposed heliocentrism thousands of years before Copernicus came along. But Aristotle had a clear refutation to that argument, which was based on logic. As I mentioned in last class, and I've been taking a while to say it here today, if Earth were to move around the sun, Earth would change its distances from the sphere of background stars. And what Jonathan was reminding us of is that would mean that the angular separation between two stars, let's say it's 5 degrees between the end stars and Orion's belt, that angle would change when Earth moved to some other part of its orbit. It would be some angle smaller than 5 degrees, and that the stars should kind of wiggle around in their positions. Yet, Aristotle argues, we have never seen any stars shift their positions. Therefore, the Earth cannot be moving. Last time we also talked about the faulty assumption in this argument. Do you guys remember what the faulty assumption is? This is an argument that's good and it's based on geometry, but it's ultimately incorrect. What did Aristotle get wrong? I need to know that you guys understand this before we go forward here.
How small we were to the rest of the universe?
Kind of.
Didn't he think that he proposed that we were the center of the universe?
Yes, but I'm telling you what his most profound argument was, that we were the center of the universe. In other words, go ahead.
No shift in the position of the stars, so that means the Earth didn't move.
Right. So is the Earth the center of the cosmos then? Is Aristotle correct?
No.
No. But his geometrical argument is sound. So what's the problem?
He didn't take into consideration how far away things are.
How far away? What was he in? Sorry?
The stars in the background are.
Right. And I think Jonathan was trying to say that, but I wasn't 100% satisfied. Yes, Ian, that's what I wanted to hear.
About gravity?
Oh, gravity wasn't even a shadow of a thought. Well, actually, Aristotle did come up with the term gravitas to explain why things wanted to stick towards the center of the Earth. So I don't want to say that gravity wasn't a shadow of a thought, because Aristotle had coined a term, gravitas, although it was very different from the gravity you're going to learn about next week. Next week is going to be a hell ride, so hang on to your hats. But to finish my argument, the reason why Aristotle got the problem incorrect is just as Ian says. Aristotle assumed that the stars were on a sphere that was just past the orbit of Saturn. In reality, there is an immense gulf of space between the planets in our solar system and even the very closest star. It would have been insane for Aristotle to consider that there was this huge gap of empty space before you got to the wall of stars. As a matter of fact, parallax does exist, but it is an extremely small and delicate measurement to make. It wasn't until we developed very powerful telescopes, and even today you can spend an entire year observing a star with a very powerful telescope to even try to see this parallax. I was just thinking that maybe a nice thing for you guys would be, I do have a slideshow from my stellar system class with a little kind of animated GIF of parallax. I think you guys get the point, so maybe I don't need to just keep beating this here, but just for funsies, let me share with you this little animation. If you could watch the stars very carefully, slide 16, for a full year, as Earth rotated around the sun, this is what you would see the stars do. You would see them shifting their angular position. Now, the reason why some shift a lot in angle and some shift only a little has to do with the fact that stars lie at a variety of different distances from Earth, right? In Aristotle's day, they thought the stars were all fixed on the same sphere. In reality, there are close nearby stars and there are more distant stars. And the closer you are to the sun, the more the motion of Earth will cause this parallax effect. So let's remember that good vocab term, parallax. If you weren't here last time, you can reproduce parallax by holding your thumb outstretched and blinking your eyes back and forth. You can see your thumb doing a parallax shift. Okay. I'd like to also remind you that the Greeks, through their greatest astronomer, Ptolemy, constructed a foolproof, well, almost foolproof, working model of the Greek solar system. Not only had they convinced themselves that Earth was the center of the cosmos, but they had also constructed a very elaborate model demonstrating how the planets should rotate. And you'll remember that Ptolemy constructed a geocentric universe with what are these things called again, guys? Who knows their vocabulary terms? What's up with these little secondary circles that the planets are rotating on? Who remembers what those were used for? No? Jenna?
Are those the epicycles?
Yes. And why do we need epicycles, Jenna?
They describe the retrograde motion.
Nicely said.
Yeah.
Beautiful. Planets, you will remember, from time to time do a kind of wobble across the sky. Where's the picture of it? Here's one picture of retrograde motion with Jupiter. And you can see that usually planets drift eastward along the ecliptic night after night. But every planet goes through a period of maybe a week or two where it stops moving eastward and night after night temporarily moves westward, and then back again. This would have been maddening to Greek philosophers. Remember that these planets were their gods. They were polytheists. Why would the gods be drifting eastward? That's weird enough. And then suddenly change their mind, try to move westward, and then move back again. They probably thought that if they could build a working model of the solar system or the cosmos, it would be akin to understanding the minds of their gods themselves. So this was important stuff. Also, remember that the history of astronomy is tied in with that other least favorite subject of mine, astrology. And astrology and astronomy went hand in hand for thousands of years until people realized that one of those things is useful and the other is not. Not everyone got the memo, apparently. Okay, so the Arabic Greek mathematician and astronomer Ptolemy built a perfect geocentric model with over 100 epicycles, all simultaneously rotating. And he wrote this book called the Almagest, in which he could explain to you how the planets moved and would predict their rising and their setting times and the times of eclipses and other such things. And because it worked for a while, people thought that they understood the heavens. And then thousands of years went by. And after thousands of years, Ptolemy's predictions for the rising and settings of the planets started to become unhinged. First, eclipses would be an hour late, then they would be a day late. And people began realizing that this model could not describe the entire story. Notice that Ptolemy is around maybe 100, 200 Common Era, as we say now, and we're about to make a big jump in time forward to the Copernican Revolution. Nicolas Copernicus, notice the date here, maybe around 1500 or so, was what we would think of as a sort of Renaissance or, a Renaissance scientist. After the Crusades, people began returning from Arabia with all of these old ancient tomes, books by people like Aristotle and Aristarchus and Pythagoras. These were works that were kind of lost to time as Europe went through its infamous Dark Ages and learning was lost for a great period of time. But not only, oh, my internet's getting weird here, so. Not only did the model of the cosmos cease to function properly, but also all of these books were returning from Arabia with hints about philosophers who were interested in studying the motions of the planets and the stars. Stepping into that scene is a legendary fellow, Nicolas Copernicus, a Polish astronomer, who had the brilliant idea that he could make a better model of the solar system by placing the sun at the center of the cosmos. Historians have debated whether he might have seen a book or a tome by Aristarchus, and maybe he got the idea from that ancient Greek philosopher. But there's no writings and no way to be sure. He could have been just independently came up with the idea. Let's take some notes, okay? We are now going to move into a new sort of framework of thinking here called heliocentrism. Let me see. I guess I'll play this marker out just a little bit more. Heliocentrism, as the name suggests, is the theory that the sun occupies the center of the solar system. And the person we have to thank for this theory is the famous Polish astronomer Nicolas Copernicus. And he was operating around the year, I'm going to say 1500. You know, when I grew up, people said AD and BC. Now they say Common Era and before Common Era. I actually approve of that secularism, but it's still just, this seems more natural to me. So Nicolas Copernicus was a Polish cleric. That means you're not really a priest, but you're sort of like some kind of mathematical functionary in the Holy Roman Church. I think this was before the Protestant, Reformation or something. So they would have just been not the Roman Catholic Church, but the Holy Roman Church. And he was also a polymath. He was a mathematician, obviously an astronomer. And his most important contribution to astronomy was to place the sun at the center of the solar system. In a weird way, apparently the drive that Copernicus had to place the sun in the center of the solar system was actually because he had been reading works by the philosopher Plato, who had imagined a perfect heavens involving perfectly circular orbits and idealized spheres. Copernicus argued to himself that Ptolemy and friends had put so many rotating spheres inside of spheres that they had lost the elegance and the simplicity of the Platonic universe. People would have to try to track the motions of stars and planets with very complex devices like this armillary, which would have rotating disks within rotating disks. It was extremely complicated to try to map out the movements of the planets. On a fun note, and this is just a kind of fun thing, I recently read about this thing that was discovered on a Roman shipwreck, maybe around the time of Julius Caesar. It's called the this is just some cool anti-Kythera mechanism. And basically they found this old Roman shipwreck that was carrying treasures to Rome for, I don't know, Julius Caesar or some other famous senator. And the ship went down at sea and was lost for thousands of years. When they finally unearthed it, they found this wooden box with this sea-encrusted, rusted-up mechanical clock. The amazing thing about this was this predated any type of mechanical watch by hundreds and hundreds of years. And people wondered for a long time what the purpose of this elaborate machine was. And they eventually realized that it's probably used to map the motions of the planets using the Ptolemaic solar system. So people have tried to reconstruct the machine, showing all of the rotating disks and gears. And they even have like a model of one with planets rotating around. Very cool stuff. So you read the Wikipedia page on that if you're ever bored. It's very interesting. Copernicus was worried that this model no longer worked, and it was also just painfully confusing. Wouldn't it be cool, he argued, if we could return to a more elegant solar system where the planets moved on perfectly circular orbits? And when he placed the sun at the center of the solar system, he discovered that he got a cool benefit that he wasn't at first anticipating. Not only did the solar system look simpler and more elegant, but he now discovered that he had a better explanation of retrograde motion. And this is the true explanation of why planets go into retrograde. So let's take a look at this diagram and see what's up. The blue dot obviously represents Earth moving around the sun. The red dot represents Mars. In configurations 1, 2, and 3, both Earth and Mars are moving eastward along the ecliptic and traveling around the sun. The Earth, of course, is on an inside track, so it's going to move faster than Mars. And as it catches up to Mars, we can see Mars drifting to the left, which is eastward. And then when Earth starts to pass by Mars in positions 4, 5, and 6, we have basically what is a similar effect to parallax going on. Because we travel past Mars and go past it in orbit, we temporarily see its position shifting backwards with respect to the background stars. This is a version of parallax. And then as Earth and Mars march forward, we can see Mars moving forward again. So retrograde motion is simply explained in terms of Earth just lapping the other planets in its orbit. Let's put that in our notes because that's kind of important issue. He had a new description of retrograde motion. And it's, of course, the correct one that we know works today. Now, as I mentioned, Nicolas Copernicus was a functionary, some kind of accountant or number cruncher in the Holy Roman Church. And remember that when people like Plato and Aristotle were debating the motions of the heavens, there was no Christianity. It just didn't exist. Christianity was invented afterwards by the Romans, okay? And in the intervening years between the time of the Hellenistic Greek philosophers and Copernicus and the Holy Roman Church, the church became not only a spiritual body, but basically the #1 political entity that controlled most of Europe. It was a military and a governmental body as much as a religious institution. In the thousands of years between those two time points, there were philosophers and thinkers in the Christian church that attempted to justify the existence of God by using the logic of Aristotle. So famously, St. Thomas Aquinas or St. Thomas Augustine, they were two of the big ones. They were learned scholars who had studied Aristotle, and they attempted to prove that God existed. Remember the Aristotelian syllogisms that we talked about? If A implies B, if B implies C, then A implies C, right? That's an idea that Aristotle came up with. The problem with using Aristotle's philosophy to justify the existence of God is it had the unattended effect of backdoor deifying Aristotle and making him every bit as important as any one of the gods that, or the one God that they worshipped. And Copernicus was no dummy. He knew that if he were to tell people that the sun was the center of the solar system, it would be the equivalent of saying Aristotle didn't know what he was talking about when it came to the heavens. Obviously, that was not going to be a well-accepted proposition. So although Copernicus did write up his theory of a sun-centered solar system in a legendary book called De Revolutionibus Orbium Celestium, on the revolution of the heavenly spheres or whatever, he didn't publish the book until he was laying in his deathbed. And he waited until just before he died. They say that he was like laying there in like this terminally ill bed, and they showed him the proofs of the pages. And he even wrote a little foreword to some of his friends that were going to read the book. And he said, some of you may find this a little bit disconcerting, that the sun is the center of the universe and that Earth is no longer the center of the universe. And that could be troubling philosophically, but don't worry about it. Maybe it's just a mathematical model. Maybe it's not really true. Maybe this is just a convenient mathematical model. And by the way, check out my new description of retrograde motion. Pretty hot, right? And then Copernicus died and checked out, and people were sitting there with this book wondering, what was the correct interpretation of the heavens? Was the sun the center of the universe, or was the Earth the center of the universe? And thus began the great debate that ravaged astronomy for years: geocentrism versus heliocentrism. Which of these two models of the heavens were correct? One of the reasons people had a difficulty accepting Copernicus's sun-centered solar system is Copernicus made a fatal flaw in his model. Because he was once again influenced by Plato, who had argued that the motions of the heavens had to be perfectly circular, his insistence on using perfect circles for the orbits of planets meant that even Copernicus's model didn't perfectly predict the rising and the settings of planets or the times of eclipses. So people could rightly say, Copernicus, you think the sun's the center of the universe? Well, look at your shitty book. I can't even predict this eclipse any better than Ptolemy could, and he was around 1,000 years ago. So this led to sort of difficulties, not only philosophically, not wanting the Earth to be the center of the solar system, but also the fact that the predictions of the model weren't good. Now we introduce a new philosopher, a person who came after Copernicus, and his goal, he sort of steps into the scene with the desire to solve the great debate, which model of the heavens were correct. And let me introduce to you a famous astronomer you may never have heard about. His name was Tycho Brahe, and he was a Danish astronomer that lived shortly after Copernicus and is considered by modern astronomers to be the greatest naked eye astronomer ever to chart the positions of stars. Tycho Brahe was the last major astronomer to do astronomy without the use of a telescope. And apparently he did a pretty good job of it. Lead notes on this guy. There's only 4 philosophers or astronomers, I guess, you need to know about for heliocentrism. Copernicus was the first. The second is Tycho Brahe. Tycho Brahe, the legendary Danish astronomer, was inspired to go into this type of work when, as a young man, he used Ptolemy's Almagest to observe an eclipse and found that it came 20 minutes later than Ptolemy suggested. It blew his mind that there was a man who lived 1,500 years before him who could predict the date and almost the time of an eclipse that would happen in his lifetime, and yet the eclipse was off by 20 minutes, and the 20 minutes drove Tycho mad. How could he have been so close but off by this small amount of time? I'm going to figure out what went wrong. Luckily, Tycho Brahe had some powerful friends. He was friends with the Danish king at the time, and the two of them would get insanely drunk at banquets and parties. And apparently Tico was a pretty cool guy to party with because he was a loudmouth and he would like fight people. He famously got his nose cut off in a duel with another gentleman over who was the better mathematician. They had a sword fight over it. Tico lost the sword fight, got his nose cut off. They replaced it with a golden nose. He kept drinking and partying. And the king said, you know, Tico, you're so amazing. You're such a fun guy to party with. I'm just going to indulge in your little pet hobby here. And I'm going to let you try to solve the debate between geocentrism versus heliocentrism. So Tycho Brahe's whole drive, his whole motivation as a character, is to determine the truth about the great debate of heliocentrism versus geocentrism. And to help Tycho Brahe do this, the king gave him enough money to build his own state-of-the-art private fantasy observatory. He gave him an entire island known as Uraniborg. And the island still exists today, but it has a way less cool name. I think its name is like Sven or something. But back in that day, here's like a little illustration of it. He built Tico this crazy elaborate observatory compound with all of these tools and houses and places to keep records. And he basically gave him an entire island unto himself. So he has a private observatory called Uraniborg. And when he went there, the whole idea that Tycho Brahe had was to very, very carefully map every single star in the sky down to a positional resolution of 3 minutes of arc. So here's another key idea. He mapped every star in the sky, every star's position down to a 3 arc minute resolution. The reason why modern day astronomers are so impressed with this is a major, very scientific undertaking of the sort that a modern astronomer would do. Carefully measuring and mapping the positions of stars. By the way, 3 arc minutes is the limit of human vision. You cannot see any angle that is smaller than 3 arc minutes. It doesn't matter if it's a galaxy. It doesn't matter if it's a paramecium floating around in your eyeball. Anything bigger than an angle of 3 arc minutes, you can usually see. Anything smaller, you can't. So he basically did the very best he could do with his naked eyeballs. And by the way, when he went to Uraniborg, he brought some friends with him. And you can see a picture of this in this famous woodcut. He brought out to the observatory a famous German mathematician who was his kind of graduate student named Johannes Kepler. And they also had a dwarf who did all of the cooking and cleaning and some of the record keeping. So here's a famous woodcut showing the legendary Tycho Brahe with Kepler and the dwarf taking measurements. He's using this cool old-fashioned device known as a Mural Quadrant. And basically, this is kind of like a big sextant. It can measure the angular positions of stars. And if you look up here at the top, you can see there's a little slot which is cut into the wall that points towards the observer's meridian. And if I understand correctly, the way this works is when the star crosses the meridian at its highest point, you can use a stick or a staff to kind of measure its angular position and thereby chart it down. The question I want to know is, do you guys understand what he was doing? Why would Tycho Brahe be mapping every star's position down to 3 arc minutes as a means of solving the debate between heliocentrism versus geocentrism?
Maybe to see if they do shift in the background?
That's right. Very good. So the whole thing that he was doing was testing Aristotle's hypothesis. What he was doing here was he was searching for parallax. Okay, This might be obvious, so forgive me, but I just want to make sure that you guys understand the arguments. If the stars shift, which model of the cosmos would be correct?
Heliocentrism?
That's right. Then it's heliocentrism. If the stars are fixed, then it's geocentrism. What do you guys think? Did he find stars that shift? Yes or no?
Probably not. If they did, he probably wouldn't be able to see it with his
Yeah.
naked eye.
No way. The star closest to us, Ian, is known as Alpha Centauri. Its parallax shift is the biggest of any star in the sky, and it's 0.75 arc seconds. So there's no effing way he was ever going to find parallax. Despite this being a brilliant program, he found no stars shifting, and Tycho Brahe, after Copernicus, concluded more or less that the Earth was the center of the cosmos. Except Tycho Brahe, while doing this, made two legendary observations that you guys need to know about. Going to erase. Is everyone okay with me erasing? I might not have left that up long enough. Okay, I don't hear any objectors. Here I go. I now want us to take notes on what are known as the two observations of Tycho Brahe. I'll just call it the two observations of Tycho B. These were observations which kind of gave him the willies and made him realize that the Greek geocentric model couldn't be exactly the way that they had described it.
I actually have a question.
Oh, I'd love to answer it. Please interact with
I'm
me.
sorry.
No, Nori,
So
I need someone to interact with me. Yes.
So I wasn't here for the lab on Monday, but I did rewatch it, and I did try and like watch it like over and over again to like try and understand. And you were talking about it like today about like the stars shifting and like the Earth being the center. And this might sound really stupid,
That's okay.
but so when the stars shift, does that mean that the Earth is like centered and that's like geocentrism?
If the
Or
stars
am I
shift,
saying that completely wrong?
I'm afraid you are. If the
Mhm.
stars move, that would mean that it was Earth that was moving, right? So I don't know if I did this demo.
Okay.
Thank you, first of all, for watching the video. What I worry about with all the students who kind of watch this later on is there's probably a great temptation to be like, fuck it, I just want to get this over with and fast forward through the lecture and just get the homework done. I know that probably happens not a little, but a lot. But the problem is, if you don't take the time to watch these lectures, they all kind of build on each other like a Jenga puzzle.
Yeah.
Yeah. So in other words, I'm glad that you're asking this question and doing it. I don't know if I did this demo, but in the parallax demo, your eyeballs are Earth at two different points in its orbit. And if you hold your thumb out, Nori, go on, be a sport and hold your thumb out. Do that. Do what I'm doing. Yep. And now close one eye and note the position of your thumb. And then when you blink back and forth, you should see your thumb do a little parallax shift. That's the shift we're talking about. And in this case, it's because the Earth is at two different positions in its orbit. Does that make sense?
Yeah, it does.
In fact, the more
My eyes are Earth.
yeah, your eyes are the Earth at two different positions.
Okay.
I can also show you this is kind of the modern version of parallax. This is a little bit different than Aristotle's because Aristotle didn't think that the stars were, he didn't know that the stars could be at different distances. He thought they were all in the same sphere. But the modern version, you know, I'm telling you about parallax because it's like a huge thing in astronomy. Astronomers use this all the time. And you can see here, Nori, if you can see my, sorry guys, I muted myself somehow. I don't know what I'm a little out of it today. Too much fun last night. Okay, in this picture here, Nori, you can see Earth at two different parts of its orbit. There's your two eyeballs. And in July, we look at the red star and we see it over here at position B on the sky. But later in January, we're at this point in our orbit. When we look at that same star, we see it shift over to position A. This is the modern version of parallax. Even though Aristotle thought all the stars were the same distance, it still was a similar kind of thing, which the stars would change their angular position. Anyways, I hope that helped. Let's talk about the two observations that Tycho Brahe made, which convinced him that even if the Earth was the center of the universe, which of course is not, that the Greeks could not have understood the cosmos the way he did, because he saw two wild and wacky things. The first thing that he saw was a comet. Now, I don't know if you guys have ever seen a comet. There have been a few in the last several years. But when you go out and look at a comet, it's not like this little faint thing that's hard to detect. If it's well, they can be, but usually a legendary comet like Halley's Comet, or let's just look at Hale-Bopp. You go out at night and you see this brilliant fuzzball on the sky. And oftentimes, like, let's look at this picture here, which is cool, because someone took a photograph of the comet Hale-Bopp over like some backyard with trees and stuff. And you see this beautiful fuzzball, and comets legendarily have two tails. They have a beautiful blue plasma tail and then a white curvy dust tail, and they just look freaking awesome. One of the first times I ever observed a comet as a professional astronomer was like years ago when I first got this job. This comet kind of showed up out of nowhere that no one had seen before, called Comet Holmes. And I don't know if you know how these work, but a comet is basically a big lump of rock and ice. And it's on a super, super elliptical orbit that brings it from the edge of the solar system inside the orbit of Earth, really close to the sun. And what happens is, as this thing starts flying close to the sun, because it's made up of ice and rock, near the sun, the sunlight heats up all of the ice, and it sublimates into water vapor. And so all of the ice just starts turning to gas, and that's what you're seeing. You see this brilliant fuzzball in the sky that's all water vapor. Because of this, sometimes people don't see comets until it's too late, and they'll suddenly just explode and appear on the sky. Probably what happened with Tycho Brahe. So the story goes that I've had this job for less than a year, and this comet shows up out of nowhere. So of course everyone wants to, let's ask our astronomer, what's up with Comet Holmes? Can we come and see it at the observatory? So that day I got wind that the vice president and the deans were all going to come to my observatory so that they could see Comet Holmes. So of course I'm freaking out a bit because I'm new on the job and don't want to look like a ditz if I can't find this thing. So I spent all day getting charts and tables and figures. I've got like its right ascension and declination. I've got its altitude and azimuth of the rising and setting times. I've got just a bundle full of papers. Like, I've got to be able to find this comet or I'm going to look like such a jerk, and why are they paying me, right? And so I'm sitting out there and I'm a little worked up, because I hadn't found this comet before. And so the sunlight is fading and all of the deans and the VPs and students are there. There's like a mob of like 100 people. And if I can't find this thing, I'm gonna look like a huge dork, right? So I'm sitting there with all the papers, and night finally descends, and I look up and I go, oh, there it is. I didn't have to do any of that shit. I didn't have to look up any tables. It was right, because the comet was just so big and bright on the sky. All I had to do was be like, behold, the comet. In other words, Tycho Brahe, observing with his naked eye, had no difficulties seeing this crazy, awesome looking thing. Here's the trouble. The Greek philosophers like Aristotle and Plato, they could not have handled this thing. This was not okay for the Greek conception of the heavens. And do you guys, anyone who was here for Monday's lecture, remember why Plato or Aristotle wouldn't have liked the idea of a comet just showing up out of nowhere? What rule would that have violated? This is a small...
I wasn't there, but is it something about having the perfectly circular orbits?
Yes, but not just perfectly circular orbits. Plato's entire argument for why orbits had to be perfect circles is that the heavens were immutable. They were not subject to change, but they were a perfect cyclical clock that never ever altered. To have this crazy, wacky comet show up out of nowhere violates all of that. In fact, there's no way Tico would have been the first person to ever see a comet, because they're so easy to spot. But if you had asked Aristotle or Plato, what's up with this comet? They would have said, first of all, don't trust your eyes because your perceptions are stupid, you know. And the second thing they would have said is, that's probably just an atmospheric phenomenon. But Tycho Brahe was so good at astronomy, he knew that thing was in outer space. He tracked it going around the sun. He was not confused about that. So there was no way that the Greek model of the cosmos could be the proper understanding if there were random one-offs. And that's part, by the way, part of his second observation. And the second one's pretty cool. He saw what we call, or what he called, a nova. And nova is Latin for new star. The way it would have looked to Tycho Brahe is one day, whoop, a new star would appear in the sky. And that totally freaked him out, because that said right there that even the background fixed sphere of stars was not immutable. In fact, Tycho had not only observed a nova, he had actually witnessed what we would call today a supernova. And because he kept a very careful record of the position of this new star, today we've gone back with the Chandra X-ray telescope and we looked at the exact coordinates of the new star that Tycho saw in the year 1572. Want to see what it looks like? Boom. That's what we found when we looked at his coordinates. This is a huge shock wave of hot plasma that's expanding in a giant sphere. Basically, Tycho had watched a star explode, and because it takes such a long time for this bubble to expand, even though he observed it in 1572, today in 2021, we can still see the bubble of gas expanding. This was a cool collaboration, but in fact, this is now known as Tycho's supernova. So what is Tycho Brahe to do? On one hand, there's no parallax, and Earth must be the center of the cosmos. On the other hand, the cosmos is way weirder than any Greek philosopher would have thought about. And gee whiz, we can't help but deny that Copernicus had a really slick description of retrograde motion. Tycho, ever the good scientist, invented a third model of the cosmos, and it's known as Tycho's model. And here's a picture from his book with probably his handwriting. You can see that what he did was he kept Earth at the center of the cosmos. So this dot here is Earth, and you can see it's in the center of the background sphere of stars. So Earth is the center of the heavens. And he has the moon orbiting Earth, and he has the sun orbiting Earth. But then he borrowed Copernicus's model, and he had all of the other planets orbiting around the sun. In a weird way, even though he left Earth the center of the cosmos, dynamically, this is kind of the same as the Copernican solar system. It's just from an Earth-based reference frame. So very cool model. And so, by the way, not only was Tycho Brahe's model the best at describing all the observations, his model also predicted the positions of planets and eclipses better than either Copernicus's or Ptolemy's. But you know what? Nobody liked Tycho Brahe's model. And the reason why is because nobody liked Tycho Brahe, because he was an asshole who would get drunk and have sword fights with people at parties. So despite him having the best science, people liked his model, disliked his model just because they disliked him. And maybe over time, Tycho's model would have become the dominant theory of the solar system had not something interesting happened. His bladder exploded at one of these elaborate dinners from drinking too much, and he got this urinary tract infection and died. And while he was laying in his deathbed, his graduate student, Johannes Kepler, who was a mathematician, he brought him to his deathbed and said, Johannes Kepler, you have to tell the world about my model of the solar system. They will come to accept it. And what he didn't know was that secretly, Kepler hated him, and Kepler was a dyed-in-the-wool Copernicus lover who just believed that Copernicus's model was right, even the hell of Tycho Brahe. In fact, so bitter apparently was their rivalry that a few years back, they actually exhumed the body of Tycho Brahe from his grave to test him for arsenic poisoning, because one theory held that it wasn't his bladder that exploded, but that I kid you not, they thought that Johannes Kepler had poisoned him just to get his orbital data for Mars. You can't make this stuff up. It's so wild. So I just want to show you here, if you ever want, like, BBC body of Tycho Brahe exhumed. Can I spell exhumed right now? Yeah. Danish astronomer Tycho Brahe exhumed to solve mystery. And this was in 2010, so about 10 years ago they did this. And so they tested his like pieces of his hair and skin to see if it had arsenic in it. And it turned out that it was mostly full of mercury, but it wasn't because Kepler poisoned them. It was because they were all doing alchemy experiments and constantly rubbing mercury on their fingers. And so a lot of great scientists of the era actually went crazy and died from that. Anyways, here's what happens next. Johannes Kepler literally steals Tycho Brahe's data for the orbit of Mars, and he fled into the forests of Germany to develop a new and even better model of the solar system. And here's where we get to the part of today's class where we have to do some work. Let me check the time here. Okay, I'm doing just fine. Now it's time to talk about Johannes Kepler. Johannes Kepler was the assistant to Tycho Brahe. He was also a German mathematician. I guess we could also say astronomer. Actually, it's kind of interesting. He was also a crackpot astrologer and mystic who had all these crazy ideas about the universe. But what's important is he loved the Copernican solar system. I'm a little tired, so I can't think of a better way to say that. But he believed, irrationally so, that Copernicus had to be right about putting the sun at the center of the solar system. He absconded with the data for Mars, so he stole Tycho's data for the positions of the planet Mars, and he retreated into the wilderness to try to make an accurate model of Mars's orbit, which he eventually did. He discovered a new model for the orbits of planets. And this is eventually what made Copernicus's model of the solar system work. You will remember that Copernicus's model suffered from a flaw, which is that he had used perfect circles to model the orbits of planets. Tycho abandoned the Platonic obsession with perfect circles, and he allowed the orbit of Mars to be an ellipse. So, and this is where we get into the business. He used ellipses to model the orbits of planets, we'll say. And this made the Copernican solar system work. Now, Copernicus's model would accurately and perfectly predict the rising, set times, and motions of planets across the sky. And it was irrefutable at that point that the sun had to be this, well, almost irrefutable, as you're about to find out. By the time Kepler came up with this, most of the professional scientists in the world quickly realized that this had to be the true description of nature. Let's talk for a second about ellipses. I'm guessing you guys don't know what that is. Does anyone know what an ellipse is? Okay. An ellipse is part of a class of geometrical objects called conic sections. Sorry, wrong slideshow. Let me show you a model of conic sections real quick. Okay, so the question is, how many ways can you slice a cone? The answer is 4. Function F567. If you slice a cone horizontally, you get a shape called a circle. If you slice a cone at an angle, you get a squishy circle we call an ellipse. If you slice a cone through the bottom at an angle, you get a kind of V shape that we call a parabola. And if you slice it perfectly vertical you get a slightly different V shape that's called a hyperbola. Circles, ellipses, parabolas, and hyperbolas are known as conic sections in mathematics. And mathematicians find them interesting. They're interesting geometrical shapes. Kepler would have known about them, but he made the bold move of saying, what if the orbits weren't perfectly circular the way Plato wanted? What if we modeled Mars's orbit as an ellipse? And pow, it all came together. Let's make a little model of an ellipse. In fact, in our lab on next Monday, we are going to make an ellipse together. And I want to give you a heads up about this so you can get the materials. Just humor me for a second. I just want to give you a heads up. So if you're out, like if you're going to a store or the supermarket, you might think of this. If you want to do Monday's lab with me and do it right, I'll need you to get the 4 following inexpensive things. A piece of cardboard. You can just cut a piece of a, wine box or something for cardboard. You're going to need just 2 push pins. Steal them off a cork board somewhere. A little tiny loop of string, maybe about, I made my string 30 centimeters and then I tied it into a knot. And we're going to build an ellipse together using these materials. If you get these simple things, you'll have a lot more fun doing this with me. So I'm mentioning it now in case you think about it while you're at the store this week. Okay. How do you use these things to make an ellipse? Let me show you a picture of what we're going to do. And then we're going to make a little cheap, cheesy ellipse on the board for now. Let me go back here. Yeah. So the way you make an ellipse is you take your 2 thumbtacks and you stick them through a piece of paper into the cardboard. And then you take the loop of string and you tie the loop of string around the 2 thumbtacks. Then you put your pencil into the string and you hold the string taut so that there's tension on it. And it makes a nice little triangle. And you just drag your pencil around the paper. And because the triangle has the same perimeter, it makes you a beautiful geometrical ellipse. This is how we're going to do it, and it will be fun. For today's lecture and for today's homework, you guys need to know a little bit about ellipses. So let's kind of make a cheesy version right now on the board. So if you have a ruler handy, bust that out. Okay. Let's make a model of an ellipse. I haven't really figured out a good way to do this on the dry erase board, so here's my cheap version. If you have a ruler, make a line in the middle of your page, leave some headroom, and make that line, let's say, I don't know, maybe 12 centimeters long, okay? I'm going to do slightly bigger here. Make this 60. And mark the midpoint of that line with a dot. So if you made yours 12 centimeters long, mark it at 6 centimeters. Now we're going to make a vertical cross, but I want it to be much shorter than 12 centimeters. So maybe make it 8 centimeters or 6 centimeters. I'm going to do something. How will I do this here? I'm going to exaggerate mine so that we really see the ellipsiness of it, okay? So make sure the vertical line is a lot shorter. And then just freehand style, we're going to kind of construct an oval, kind of like a football. This is not a proper ellipse, but it's a close approximation. Okay. Parts of an ellipse. So for us, our working definition of an ellipse for now is going to be a squishy circle, okay? That's our definition of an ellipse. And this squishy circle needs to have 2 focus points where we would have put the thumbtacks. I don't exactly know where mine should be, so I'm going to put them like 23 here. The focus points in an ellipse are called F1 and F2. Okay? This main slice is called the major axis. Let's label that. The short axis is the minor axis. And then there are a couple of parameters that we're going to be interested in. The distance from the center of the ellipse to the focus point is a number that I call x, okay? X goes from the center to the focus point, and x is the focus offset. And then there is another very important parameter. It goes from the center to the edge of the ellipse. I'm just going to clean this up here for a second. This distance here is a really important distance in this class. It gets its own letter A, and A is the semi-major axis. In other words, it's half of the major axis. There's one more parameter that we need. The parameter E, or eccentricity, measures how squishy our ellipse is. And you can actually calculate it. So I'll just kind of write this over here. E stands for the eccentricity of my ellipse. You can think of the eccentricity as the percent squishiness of your ellipse. And usually the way you calculate it is you divide x by a. So the eccentricity is x divided by a. And the domain of E is a number between 0 and 1. E can be equal to 0, but E can never be 1. It always has to be a percentage. And so usually the way this works is if the eccentricity is 0, your ellipse is not squishy and it's just a circle. If your eccentricity is like 0.5, that's kind of like egg-shaped. Sorry, I'm getting kind of down to the bottom of the board here. And an eccentricity of like 99% is sort of like a cigar. That's probably not too helpful, so I'm going to show you a picture. Just make sure you write all that down because you want to have that. This is important stuff. I expect you to memorize this, okay? I'm hoping you'll accidentally memorize it with time. Let me show you guys something. If I go to Google and I type eccentricity, there's kind of a cheesy little image that I think does a pretty good job of showing you what eccentricity looks like. There we go. So take a look at these circles with me. Here you can see a variety of different ellipses, all with varying degrees of eccentricity. The red circle is an eccentricity of 0. That ellipse is a circle. And then as the eccentricity goes from 0 to 0.2 to 0.5, we start to get egg-shaped, then we start to get kind of sausage-shaped, and then cigar-shaped. Planets can have orbits with any type of eccentricity. But let's take a look at the eccentricities of the orbits in our solar system. And we're going to just look for a data table here. 5 more rows. So you guys can see my screen right now, correct? Do you guys, part of science, part of learning to think like a scientist is being able to look at a table of numbers and draw some conclusion about it. Let's see if any of you guys are good at that. What do you notice about the orbital eccentricities of the planets that you see here? Can you come up with any takeaway conclusions? Why sip my iced tea? Based on what I just talked about the fact that, how do I do this here? Eccentricities can go from 0 to 99%. What do you notice about the eccentricities of the planets?
This might be wrong, but is it the bigger the planet is, the smaller the eccentricity?
No, not at all, because the planets with the largest eccentricities are two of the smallest. Pluto and Mercury are two of the smaller bodies in our solar system. The lowest eccentricity in the solar system is Venus,
Yeah.
and that's not as big as Jupiter or Saturn. So
Well,
I'm
it
sorry,
They're
Ian, I would
perfectly
not say.
circled.
Pardon? Who said it?
They're not perfectly circled, and that at one point or another, they'll be closer to Earth and we can see them better.
Okay, there is a best time to observe planets when they're in opposition. But let's talk about, what was the first thing you said, Jonathan? I want to really parse your words here.
They're not perfectly. They're not in perfect circle.
Well,
Their path is not completely
There-
circle.
No, none of them are perfect circles. You guys are almost taking away the wrong conclusions here.
Okay.
I have a point, but I just want to see if anyone gets the point. It's not that of course, Jonathan, none of them are going to be perfect circles. I guess I'm being kind of vague. You know,
Is it that they're all less than 0.5?
yeah,
More
but
specific,
Jenna,
more like
way freaking less than 0.5, right? All right, keep going with that, Jenna. Now be even more bold in your statement. It's not just that they're less than 0.5.
Is it that they're less than 0.9 or they're cigar shaped?
Are the planetary orbits cigar-shaped according to this? Jenna,
Well-
this is 0.05, 0.06, 0.09. Earth's orbit is 0.02. You're telling me that's cigar-shaped? Look. What do you notice about an orbit that is 0.2 eccentric? Does that look cigar-shaped to you? Not really. Even at 20% eccentricity, you still kind of look like a freaking circle, right? Okay, Jenna, so what's my point?
What was the question?
Oh, sorry. Maybe I asked it the wrong way. All right, let me tell you what my point is. Let's just not.
Well, I get, yeah.
Do you get it though?
Yeah, they're like the opposite of cigar. They're
Wicked fucking circular. That's what I wanted you to say. I wanted you to say, holy shit, Brendan, look at these eccentricities. They're all wicked tiny. The orbits of the planets are damn close to perfect circles. Venus at 0.007, its orbit is almost perfectly circular. For instance, Earth's orbit is 0.02 eccentricity, right? If I were to draw an ellipse with 2% eccentricity and then show it to you side by side with a picture of a circle, I bet if I said which one is the circle, you couldn't pick it out. An ellipse of 2% eccentricity is so close to circular, your eye can't even detect it. In other words, no wonder Copernicus and these ancient Greeks believed the orbits of planets were circles. It's almost, but not quite true. Do you know that if Mars turns out to be one of the easier planets to observe at night? If Mars's orbit hadn't been 9% eccentric, just a little bit squishier than your average planetary orbit, Kepler probably never would have discovered that planetary orbits are ellipses. He almost got lucky that the planet he had the best data for was a little bit squishier. Now it's time for us to do a module called Kepler's Laws. This might be one of the last things we have. Oh, yeah, a little bit. I'm doing okay here. I'm going to try to squeeze two things in, and then we'll do our homework. Our homework today should be really easy, guys, so it won't be as bad as last time. Kepler developed what are now known as Kepler's 3 laws of planetary motion. They're kind of a big deal. Every astronomy student needs to learn them. Yes, it is going to be on the test. I'm telling you that right now. This section is called Kepler's 3 laws of planetary motion. Kepler After he discovered that the orbits of planets were ellipses, he discovered three kind of truths about planetary orbits, and he wrote them up in a book called Harmonious Mundi, on the harmony of the worlds, okay? And the first law is called the Law of Ellipses. Astronomers love this stuff because this is like the first time that anyone actually got something right in astronomy. And so this is kind of like a big deal. The Law of Ellipses states that a planet orbits the sun on an ellipse with the sun located at a focus point. And that's pretty wild, because it would probably have been very tempting for Kepler to want to put the sun at the center of the orbit, because he was, after all, a believer in Nicolas Copernicus. But his data was too good, because Tycho Brahe was too good of an astronomer. And basically, this is the picture that he came up with. Let me show you this cartoon here, 70. Kepler realized that the planets were orbiting on ellipses, but that the sun wasn't actually at the center of the solar system. It was at the focus point of the ellipse. And so this is Kepler's first law in a nutshell here, okay? The second law describes how the planet moves around the sun with time. It's called the Law of Equal Areas. Sometimes people just call it the Law of Areas. It goes like this. A planet sweeps out equal units of area in equal intervals of time. This law was actually a diss to Plato. One of the reasons he had to put this down is Plato had described not only a cosmos with perfectly circular orbits and perfectly spherical planets, he also forcefully argued that planets obey perfectly uniform motion. That is, their angular velocities, the rate they travel across the sky, must be constant. In fact, Kepler quickly understood that that was just not true. In fact, it was a little bit difficult to explain this, because what he was discovering, and let's just look at a little animation. When the planet gets close to the sun, okay, show me your awesome vocab here. What do we call the point closest to the sun in orbit? Demonstrate your profound knowledge of astronomy to me. Point closest to the sun in orbit is called what, class?
Perihelion.
Beautiful. Who said that?
Paul G.
Oh, Paul G in the background. Whoop, whoop. And Paul G, why don't we school these guys again? What do we call the point farthest from the sun in orbit?
Perihelion. I might have pronounced that wrong.
Aphelion. As in, well, I was going to make a joke, but I'm too tired to do that. Okay, so aphelion and perihelion. The point that I'm trying to make is, when the planet is at perihelion, it travels really quickly. When the planet is at aphelion, farthest from the sun, it travels much slower. Kepler discovered that he could predict the position of the planet if he drew a line between the planet and the sun. He discovered that, let's say a planet goes from position A to position B in 2 weeks. That's a pretty big distance. Later on in its orbit, it might go from position H to I in 2 weeks. Clearly, the distance from A to B is a lot longer than the distance from H to I. But if he traced out a line connecting the planet and the sun, by magic, the area of this triangle, he divides it up into little boxes, is perfectly equal to the area of this triangle. So the planet isn't traveling at uniform velocity or traveling equal distances. It's sweeping through equal areas in equal times. And he can predict where the planet will be next, because he knows that if this triangle takes, I don't know, what did I say, 2 weeks or 2 months to accomplish, that the planet will move to position L in 2, 4, 6 weeks from now, or something like that. So it's very cool because you can predict the position of the planet. The third law of Kepler is a mathematical formula, and it's going to be a really important formula in this class. It's known as the Harmonic Law. And the Harmonic Law states that p squared is equal to a cubed, where p is the period of the planet in units of years. And do you guys remember what A is? I told you like 5 minutes ago. What's A?
The semi-major axis.
Beautiful. But now I've got to tell you something a little bit more complicated, Jenna. The semi-major axis is not only a property of the ellipse, it also turns out to be the average distance between the planet and the sun. Let's take that second definition here. A is the average distance. I'm running out of room here, so I'm just going to do sun to planet. So it's the average, sorry, my handwriting is bad when I'm at the bottom of the board here. The average distance from sun to planet, and that's in astronomical units. I don't really like that. You know what? Later on, I'm going to ask you to read this, and you guys are going to just, you're not going to say it away. Like, let's try that one more time. It's the average distance between the planet and the sun. We're going to try a sample problem with this so you can see how it works. Very, very important formula. You're going to use this dozens of times on your test. You're going to use it in today's homework. I'm erasing. I expect you to memorize Kepler's laws. Let's just write that all over again and review it. So there are, for Kepler's laws, there are three formulas that we need to use all the time. The first is p squared is equal to a cubed. P is measured in years. A is measured in astronomical units. Go ahead and write it again. You can't write this enough times. There's also two formulas that let us calculate the perihelion and aphelion distances. And I actually went past this a little earlier. Unfortunately, the sun is over on the other side now, but perihelion is a times 1 minus e, and aphelion is semi-major axis times 1 plus e. Let's write those down. When I calculate perihelion, I use peri as my variable. I don't want to call perihelion p because they'll get confused. So the perihelion distance is a times parentheses 1 minus e. The aphelion is a times parentheses 1 plus e. I wonder if I should do a sample problem or if I should just wait for the homework. Do you guys have your Casio calculators handy? Okay. Damn it, I'm not going to get to Galileo until next time. I can already see that I've used up, and you guys are probably getting fatigued listening to me talk, which is totally fair. Look at your Casio with me here. Autofocus. Okay, the buttons that we're going to want to use, and I just want to demonstrate these to you before I show you the work. Do you guys see that there's sort of second keys in orange? Let me focus even closer. This key, if you hit shift first, that's your x cubed key. We're also going to need to use our cube root, so we'll be using these two keys. And then here is x squared, and in orange, in shift mode, is square root. So keeping an eye on those buttons, let's try a quick sample problem to sort of end out our class here, just to make sure that you guys can handle this. So we'll try this. Pluto has a semi-major axis to its orbit of, I believe it's 39.5 AU. Its eccentricity is, I think, 25%. Let's just, did I do that right? Where was that? Yeah, 25%. Good on me. I want us to find the period, find the perihelion, and find the aphelion distances. We'll start with the period, okay? If p squared is equal to a cubed, we can solve for p by getting rid of the square. Do you guys know how to get rid of a square?
Square rooted.
Yeah. You can think of it as square rooting both sides. I think of it as flipping it over to the other side where it turns into a square root. Whatever. P is equal to the square root of a cubed, okay? Let's substitute in our value square root of 39.5 AU cubed. And now let's try that in our calculators together. Okay. Follow along with me. Punch what I punch, okay? 39.5. Sorry, I'm trying to get the angle right here. Okay, we're going to cube it first. So we're going to do shift, and the backspace key is cube. Okay. Now we have to square root it. So we're going to hit shift again, and then we square root. Did you guys get this? What's my answer then? Nora, you got it too? All right, you guys are too small in my window here, so. How should I round my answer?
It should be 3 sig figs, no?
Yes, that's correct, Ian. 3 sig figs.
So that would be just 248
248 what?
AU.
No. This is a
No?
magical formula. It takes AU as an input, and it pumps out a period in
Years.
years.
Right? Yeah, okay.
Put a box around that. Okay. Maybe I'll just demonstrate the perihelion so that you guys can take a little break. Did anyone have trouble with that or want to ask me a question? Or I think that's simple, but I don't know if you guys think that's simple. Sometimes simple to me isn't simple to you, all right? So perihelion, we're going to do A times 1 minus E. So that's 39.5 AU times 1 minus 0.25. Okay, punch along with me. I want you to just do it the same way I do it. Clear it out. 39.5 times open parentheses 1 minus 0.25 close parentheses equals. Is that what you got?
I think you put 39.8 in there
Oh.
originally.
Sorry, I'm a little tired today.
No, you're fine. I just thought I'd let you know.
39.5 times, let's try that again. 1 minus 0.25 close parentheses. That does the parentheses, and then you hit equals. All right. What do you want to round it to? How about 30 AU? Famously, Pluto actually comes interior to the orbit of Neptune. That might lead some people to wonder if Pluto could ever potentially crash into Neptune in the future. That probably won't happen, and I'll explain why at a different time in our class. Okay. You learned a lot today. I wanted to get to Galileo, but I screwed up. I dithered around too much. What do you say we do a little break? I'll get a snack, get some coffee, and then we will do the chapter 3 homework. You ready for that? All right. Let's use iPhone time. My iPhone says 1:31, so a little bit after, right around 1:45 or 1:46 or whatever. That's when we'll get back together. I'll see you guys then. I thought I was recording, but I guess I am now. We're back. It's time to do homework number 3. Please make sure that you submit the homework to the correct slot. When I graded this Sunday, I noticed people were submitting homeworks to like the wrong submission. If you did that, then you probably got a 0. So I'd hate to have that happen to you. We are going to follow along with chapter 3. Ian, do you have the problems handy? Does anyone have those numbers ready to go?
I can pull it up in just a second. You said it was 3, right?
Yep.
All right. We are doing 48, 49, 52, 53, and 54.
52, 53, 54?
Yes.
Okay, Ian, are you down to read us one?
Sure.
Let's start with chapter 3, number 48.
All right. 48 says Chinese calendar.
Oh, this is a fun one.
The traditional Chinese lunar calendar has 12 months in most years, but adds a 13th month to 22 of every 60 years. How many days?
Just pause for a second. I want to make sure I get that down.
Okay.
Famously, the Chinese calendar is a lunar calendar. Remember that our calendar is based on the tropical year, the time between spring equinoxes. And there's 365.24 something days per year. The Chinese demonstrate that you can also make a calendar based on phases or cycles of the moon, and it's every bit as effective as keeping calendar time by the sun. And that's why this is kind of a cool exercise to show there's no right way to do it. There's just multiple ways to do it. Now, Ian, you said 13 months out of how many years out of 60?
It says 22 out of every 60.
22 out of 60 years. So let's do the math here. That would mean 38 out of 60 would have a 12 month. Right? Sure.
Should I keep going?
Yeah, sure.
I can wait.
No, I was going to make a point, but it's stupid. Just go ahead.
Okay. All right, where was I? 13th month, 22 out of 60 years. How many days does this give the Chinese calendar in each 60-year period? How does this compare to the number of days in 60 years on a solar calendar? And based on your answers, explain how this scheme is similar to the scheme used by lunar calendars that follow the Metonic cycle.
The Metonic cycle is a cycle of a lunar cycle based calendar. Hold on a second. So they want the number of days in 60 years. Now, didn't they give us some conversion factors to work with? I remember there are some conversion factors.
Well, what it does, I don't see anything else in 48, but it does say in parentheses at the base of it, it says, hint, you will need the data given in problem 47.
Okay, so let's look at that problem 47 and see if we can get some data out of it. I think it's 2 conversion factors. 1, we need the number of days in a month, and 2, we need the number of days in a tropical year. So here, the length of our calendar year, if you guys are looking down here, This is a tropical year, 365.2422 days. And the cycle of phases, the synodic period of the moon, is 29.5306 days. So let's get those down. 2422. So for what's called a tropical year, 1 year is 365.2422 days. I use little d for days. For a synodic month, remember the synodic month is the time between phases of the moon. 1 month, MO, is 29.5, what's we got here? 306 days. So these are conversion factors we're going to need. Okay, we have to find the number of days in 60 years. And what were the 2 follow-up questions, Ian? Sorry, I'm not. My 10-gallon hat's feeling 5 gallons flat today.
I am there with you.
Right.
Oh, you have it, I guess.
Um,
Unless you'd want me to read it.
no, it's okay. How many days does this give the Chinese calendar? Then we have to do how many days are in the solar calendar. And the third part is explain how this scheme is similar to other lunar calendars using the Metonic cycle. We may or may not answer that. We're just going to do number of days in 60 years, first for the Chinese calendar, and then for the Western solar calendar. Okay, Ian, how should we go about doing this? The procedure seems kind of straightforward to me, but there's a little trick here. Let's start with the Chinese calendar. How can I compute the number of days in 60 years for the Chinese calendar? What will I do? You're muted. Do you know that you're muted?
I did not know that. Sorry.
Okay.
I said you might want to find the number of days in the 12-month years, the 38 of those, and then the number of days in the 13-month years, and 22 of those, and then add them all together.
That's one way to go about it, Ian, and that would work. Can I suggest an even smoother method?
Please do.
Since it's a straight conversion from months to days, what if we just find the total number of months in 60 years? Then we can, that would work too, right? Well,
Yes.
both ways are effective. It's okay. So I'm going to say for 38 years, let's try to make this look like dimensional analysis. 38 years times, for 38 years, we get 12 months per year. Notice that years cancel out. Plus, for 22 years, we're going to be using 13 months per year. Years cancel top and bottom. How many months is that, folks? Punch that up for me. Remember that punching is a you job. Who's out there in Troll City today? I haven't checked on the trolls in a while. What kind of trolls we talk? Oh, Nori's back. Cool. I got Jamie, got Ryan, Zachary's hiding in there, Daniel, Paul G, always in the house. Naomi.
Would it be 720 months?
That sounds good to me. And Paul G, since I don't often call on you because I don't see your face, what about what if you helped me do some dimensional analysis? Remember that it's always important. Paul, you took my astronomy 1020 course, right?
Yep.
And you, from what I remember, seemed to know what you were doing. So actually, maybe you're not that fun to call on. Although I like the sound of your voice, I think that you can do dimensional analysis. I want to torture these other guys who are newer to my methods here. When the test comes, and it will be coming in a few weeks, guys, you're going to need to be able to do dimensional analysis on your own. So Nori, my favorite friend, who's eating a snack, Nori, you're going to help me do dimensional analysis, real easy thing here. And I want you to help me convert months to days using that conversion factor. Now, if you know how to do it, great. If you don't, let's reread the steps of dimensional analysis.
I was like secretly hoping that you weren't gonna pick me.
So
the
like, person I always pick is the person who's secretly hoping that I won't pick them. Actually, Nori, the reason I picked you partly is because you were the first box or the last box on my row here, but also because since I don't interact with you quite as often, I don't know if you make the Monday sessions or you watch them later. I
actually work on Mondays, so I can't really. And Wednesdays, like now my Wednesdays are like free, so I should be here like every Wednesday. But Mondays I really can't.
Okay, no, I get that. And that's fine. That's why we do this asynchronous. But one of the reasons I take the time to do these live sessions versus just say, hey, watch the video and I go and take a nap, is that you kind of need me to make you a little bit uncomfortable and force you to do the problem. Like, that's actually really helpful. You just have to trust me. That so Nori, it's good that you didn't want to be called on. That means you're the perfect person for the job. So okay, do you know what to do? Yes or no?
Not really. I was hoping to like solve another question, like watch it, and then.
Do you have your notes? Do you have the 4 steps of dimensional analysis? You probably have a notebook there in front of you, right? Go back to one of the first lectures. It's probably like the first or second lecture we ever had.
Oh.
You should have a section that says 4 steps of dimensional analysis. And I made
I did this. I did this with you the last time.
Oh, sorry. I have a question. I keep punching it in. I keep getting a different number.
Oh, not 720?
I keep getting 742. I don't know. It could just be me.
No.
I also was getting the same thing.
Okay, cool.
Well, guys, okay. Let me explain how the etiquette of this works. The reason why you all punch is anyone, including me, can make a mistake. So if your number doesn't agree with the number you see, you let me know right away. And then what we do is we use consensus. If multiple people are getting, the most important thing is that I don't have to punch, okay? Because I already know how to punch. That's why I've got this job here. So what did you say the correct answer was then?
742 months.
Yeah, okay. So that's fine, made a little mistake. Okay, so 4 steps of dimensional analysis, Nori. What's the first step say?
Write down the number to convert with its units.
Okay, so what number should I write down here?
Which one are we doing?
We're trying to convert the number of months in the Chinese calendar to days, right? So we just found out that there are 742 months in a 60-year period for the Chinese calendar. So what number am I trying to convert? Take a guess. Just pick one of the numbers on the board and just guess.
What number are we trying to convert?
Yeah. Well, so one of the reason why there is a step 1 to dimensional analysis is sometimes people don't even know how to get started. That's in itself a problem. So where we were when we just tuned in here is I tried to convert, or me and Ian converted the number of months, and we figured out how many months there are in a 60-year period. And we discovered that in a 60-year period, there are 742 months. Now I'm trying to find the number of days in those 60 years. So I'm converting months to days. Step 1 is write down the number to convert with its units. So what should I write down?
720 months.
Not 720. We had a typo.
I mean 742.
Good. So fine. That's step 1. You write down the number with its units. Okay, what's step 2?
Multiply by a division bar.
Fine, that's easy. What's step 3?
put the units in first to cancel out.
Okay, so give me some units top and bottom. That's your job.
I would imagine that there would be months on the bottom
Yep, that way they cancel.
to cancel out.
And what am I trying to convert
And
it to?
you're trying to convert it into days.
Okay, so we'll put
So
days. Okay, so that's step 3. We kill off the months, we get days. What's step 4?
the number in second using the conversion factor. That's what I wrote.
It's put the numbers in second.
Okay.
Put the numbers down second. You should fix that if there's a typo. Put the
Yeah.
numbers. The idea, the short version of dimensional analysis is units first, numbers second. That's the key. That's the whole secret. Okay, so give me some numbers top and bottom, Nori. You need a conversion factor, which you have.
You can put 1 on the bottom
1 month.
and 29.5306 on the top.
Correct. That wasn't so bad, was it?
No.
You guys need to be able to do this, but I need you guys to get to a point where you can even do this without me, okay? Without me kind of poking you and pushing you forward. All right, punch them up. How many sig figs are we going to keep, Ian?
I want to say 6.
Yeah, why not 3? Why were you not worried about this?
Well, because the days factor has 6.
Wait. Okay, since when did I ever teach you that you go with the highest precision number? What I'm about to do is I'm going to take you in a circular loop here.
Please.
So you've clearly forgotten the rule, Ian.
Yeah.
The rule is the shittiest number in your calculation
Right.
limits the quality of your answer.
Yeah, I remember that.
So I was assuming that you knew that, and I was asking you, why did you go with 6 sig figs and not 3?
I don't know. I guess my logic was that it's of all the numbers in it has the most significant figures. I mean,
No. So yeah.
Notable numbers.
Does anyone understand first of all, you are right, Ian. You are going to go with 6, but I wanted to see if you understood why. Jenna, do you know why? Why is the precision here and not there?
Actually, sorry, my heater's turned on. I thought I knew what you were saying, but I thought you were going to go with 3 sig figs because it's less accurate.
That's right, Jenna. See, this is what I wanted you to be thinking. And now I'm going to tell you why that's not correct. Normally, Jenna, you would go with the weakest number. But Jenna, we have to stop and think. Is this a measurement? We quickly realize it is not. We define, Jenna, exactly 12 months for 38 of the years and exactly 13 months for 22 years. Do you see what I mean? It's an idealized conceptual 13 months. Since we got this number from that 13 and that 12, this is exactly 742 months. It's a perfect number. This is the measurement, however, and this has a limiting precision. Did that make any sense? I wanted to show you this. All right. Anyway, 6 sig figs. What's my answer?
So I'm sorry. Are you picking it because it's more precise?
That's not okay.
I'm sorry.
No. This is important. This is something I can teach you, and this is a valuable skill that employers care about. You have to know where the limiting precision, you have to know where the crappiness sneaks in, right? Where is the bad?
Lower number?
Normally, it's the lower number, the number with less digits in it. But this number is not polluting the answer because it is exactly 742 months. In a way, it's kind of like saying 742.000000000 months forever. Why is it infinitely precise? Because I define exactly 12 months in a year. It's not like 12 has been rounded from, it's actually 11.297 months. Do you know what I mean? It's an even division. Like for instance, if you have a pizza and you divide your pizza into 8 slices, that's an equal 1/8 of the pizza. The 1/8 isn't a measurement. It's, you know what? Just forget about it, Nori. Just give me sig figs. Just give me 6 sig figs.
I understand it. I think I
Second explanation
understand.
helped a lot.
This is important. You got to know where your
Yeah.
bad apples are. Okay, give me your answer. Anyone?
21,911.7.
And the units?
Days.
Okay. So box that. That's for the lunar calendar. Now let's see if we can more quickly than that do the solar calendar. I'm going to need to make some space, so I'll go back up here. The Western solar calendar is much easier because we have the conversion from days to years. So we're going to do 60 years, and let's do it dimensional analysis style. Years on the bottom, days on the top, 365.2422 over 1. Okay, punch it up for me. How many sig figs am I going to keep?
Seven sig figs.
Now I'm going to play another twist on you, Jenna. Yes, you can keep 7 sig figs, but I'm going to ask you to round it back to 6. Do you know why? Since I'm ultimately going to compare it to a number with 6 sig figs, the 7th digit isn't going to be helpful because it won't be meaningful to compare. So what do you get to 6 sig figs?
I got 21,914.5.
And the units are days, right? Let's label this. This is the lunar calendar, 60 years. This is the solar calendar, 60 years. Now we have to compare the two. I'm now going to show you some next level comparison skills. Let me make a little spot here. Students, when we have to compare two really big numbers that are, you guys can see that they're only off by a couple of days out of 20,000. So these are wicked close to each other if you think about it. Maybe being off by a couple of days is a big deal, but not if it's out of 21,000. When you have two numbers that are really close, a cool way to compare them is to calculate something called percent error. Let's write the formula down for the percent error. One way to look at it is it's your value minus the true value divided by the true value. In other words, you take the difference of the two numbers and then you divide it by one of the numbers, whichever one is more true. In this case, it's not really clear which is the true number. It's the difference over one of the numbers. So let's do 21,914. Sorry. Wow, my brain is not good today. 21,914.5 days minus 21,911.7 days divided by 21. We'll say that the solar calendar is the true one, which is a little bit Western chauvinist, but whatever. Okay, 914.5 days. And you should probably put parentheses around those. Okay, class, tell me what you get. Talk to me, Ian.
So it's in scientific notation for me.
Ooh,
So,
we can't handle that, can we?
well, I just need to think through it for a second. So
Why don't you just give me the answer, round it to 2 sig figs, and just give me the answer in scientific notation.
sure. Okay, so that would be, I guess, 1.3 to the -4th. That's what it
Always
says.
say times 10 to the -4.
Yeah, okay. Good. I'm not used to, I got this calculator later.
Are there units?
There should be days, I believe.
False.
No, okay.
Why not?
Um,
Ian, what
Percent?
units? Well, hold your horses there, cowboy. We're trying to get there. Days minus days has units of days, correct?
yeah, but then divide it out by days, yeah.
And then you divide them, they're gone.
Okay.
It's not a percent yet, it's a decimal fraction. No unit, Paul G, exactly. Now, prove to me that you know scientific notation. Tell me how to write that out longhand. I'll get you started. 0 point. Now take it away, Ian.
Well, it should be 3 zeros and then 1 3.
Right. So this is the 4th place.
Yeah.
So exactly 3 zeros, 1 3. Okay. It is still not a percent. It is a decimal fraction. How do I turn it into a percent?
You have to move the decimal place 2 times to the right.
So what is my percent?
0.013%.
0.013%. Now really impress me and tell me how to say that in English. How would you say that number in English?
That's a thousandth, so 13 thousandths.
13 thousandths of 1%. Nicely done. Are these calendars close? They are 13 thousandths of 1% off from each other, meaning we don't have to keep a calendar by the sun. It is perfectly valid to worship the moon and design your calendar based on lunar cycles. The Chinese calendars are based on lunar cycles. The Arabic calendar that keeps track of the cycles of Ramadan are lunar calendars. So are the Jewish calendars. Throughout history, there's probably been just as many people who keep calendars by the moon as there have by the sun. The people who are biased towards the sun, if you think about it, are not only Western people, but that probably goes back to Egypt and Mesopotamia, right? Ra was a god. If you were an Egyptian, the sun was your god. It's pretty wild to think about. Okay, I'm going to erase this. Does everyone have it?
Wait, so in like ancient Egypt, they used to like go by that, like the lunar calendar?
They wouldn't, ancient Egyptians would not have kept a lunar calendar because they worshipped the sun as a more superior god. I was just trying to, this is a big topic and it's really cool, like the history of archaeoastronomy. Like, I just think it's interesting to think about how things like our calendar are ultimately based in the fact that people thousands of years ago were worshiping different celestial bodies as gods, and that's today why we keep a solar calendar, right? It's so,
yeah.
I know I've read that the ancient Egyptians knew that there were 365.25 days in a year. Like the ancient Egyptians knew there were not an equal number of days in a year, which is pretty cool. So they kept the solar calendar, but if you went across the moat there to China, then they would have been keeping lunar calendars. Okay, I'm going to erase. That's a topic we could talk about for hours, but I won't do that to you guys. Also, my knowledge has limits too. All right, 48, well, bam. Chapter 3, number 49. Nori, why don't you read that one for us? Do you have the questions handy?
I can pull it up.
Okay. Just, right click that PDF right here and tell me what you got.
Sorry, it just logged me out.
Mm-hmm. Everyone else get those questions handy because I'm going to want you all to read sooner or later. Is it Dragon? Nori?
No, I'm just pulling it up. Question 49.
Uh-huh.
Method of
Eratosthenes.
Eratosthenes.
I'll tell you guys a funny story. I used to call him Eratosthenes. And one year, one of my students actually had a lot of study in Latin, and they were like, "Psst, it's Eratosthenes." So I didn't know either. Okay. The method of, it looks like Eratosthenes, but it's Eratosthenes. You guys remember who Eratosthenes was, don't you? What is he famous for doing, class? What did he famously do?
You found the circumference of the Earth.
Using only sticks and the sun. Let's draw the picture together. Take a roll of tape or something that you can make a circle with. Nori, I'm going to have you read after we make the, sorry, make the diagram and then you can read. All right. We're going to have two cities, an Alexandria and a Syene. Make a line from the center of Earth through the first city and poke a little stick out of the top of Earth, and then make a line to the other city of Syene and poke a stick out of Earth. This will be Alexandria and this will be Syene. Remember that in Eratosthenes' day, since Syene was a more southern city, the sun could actually reach the zenith at noon. And he knew that because he could see the bottom of a well. Therefore, if you put a stick in the ground at noon on the summer solstice, the stick will not cast a shadow. That means the sun is directly over your head. The genius of Eratosthenes was to realize that all the rays of sunlight which strike the Earth all have to be parallel to one another. And if that's not obvious to you, well, check this out. I wanted to say this the other day, and I should have done it this way. Let's say this is the sun, and let's say this is the Earth. Oops, I'm going to try to move that. Yeah. The sun is an isotropic emitter. That means every point on the sun's surface will kick light off in all different directions. So if I were to just pick that point, there are rays of light emanating from the sun at every point in all directions. Photons are going everywhere. Now, this ray of sunlight is going to strike Earth because it points towards the Earth. And this ray, which is also parallel, is also going to strike Earth. Let's imagine you had a ray that was close to this one, but was not parallel. It diverged by 1 degree, or even half a degree, or a tiny fraction of a degree. As that ray of sunlight traveled over the course of 1 AU, that tiny angle would eventually diverge so much that the ray would not hit Earth. Therefore, Eratosthenes understood that all rays of sunlight that strike Earth have to be parallel to one another. And that, of course, means that this ray here is parallel to that ray. You will remember this is important because Eratosthenes famously measured the angle between the zenith and the sun. In class last time, I called that theta. I told you that that angle was equal to this angle theta by geometry, the distance between the two cities, and that the ratio of theta to 360 is the ratio of this distance to the circumference. And therefore, I derived this formula that we call the method of Eratosthenes. The circumference of a planet is 360 degrees over theta times the distance. And now, Nori, we're set up for you to read the problem. I would like you guys to include that diagram, if that's not too much to ask.
Do you want me to start reading?
Yes, please.
You are an astronomer on planet Earth, which orbits a distant star. It has recently been accepted that Earth is spherical in shape though no one knows its size. One day, while studying in the library of a LECT town, you learn that on the equinox, your sun is directly overhead in the city of Nain, located 1,000 kilometers due north of you.
Okay, so
On the equinox,
the distance between the two cities is 1,000 kilometers. And then keep going when you're ready.
on the equinox, you go outside and observe that the altitude of your sun is 80 degrees. What is the circumference of Earth? Hint, apply the technique used in Eratosthenes to measure Earth's circumference.
Okay, there's a little trick here, guys, but you have to be paying close attention. They gave us the altitude of the sun in the city Alec town. The altitude of the sun in the city Alec town. So what do you think I should do? Can I take that 80 degrees and plug it into this angle here? Is that okay?
Yeah.
No, it's not.
No? Why wouldn't it work out? Oh, because it's not the same?
Because, oh my God. Sorry, I just choked on some spicy rice. Okay. In the diagram, Nori, you can see that theta is actually the angle between the zenith and the sun. Let's imagine you were standing on the ground in that city. Here's the ground. Here's your zenith. That's the point overhead. And let's say the sun is coming in at an angle like so. Theta, so this goes to the sun. In my diagram, theta is the angle between the zenith and the sun. But they gave us the altitude of the sun. How does that factor in here? Does anyone see what I'm trying to say?
I guess that it doesn't plug directly in, but it's one of the lines that helps make up the angle.
Yeah, the trick here is to understand the term altitude. What does altitude mean?
The height above the horizon.
Very good. So where would that be on this diagram then?
The zenith?
No, the zenith is different than the horizon. This is the horizon, right? Nori, you knew the definition of altitude. It's the degrees above your nearest horizon. It is not the degrees next to your zenith. Theta.
Well, that would just be the point, like, because there's not really any points. It's just like the angle at which the sun hits it, and you're just measuring the angle.
And we need this angle, but I'm here to tell you that's not the angle that they provided us with. They did not give us theta.
Would we subtract 80 from 180 being the horizon?
Or
Not
wouldn't you do it from the zenith? And because the zenith is the 90-degree angle, so it would be a 10-degree between that and the angle of the sun.
Oh, okay, you said that not in a way I liked, but you came up with the right answer. Here's what I wanted to have you say, guys. I wanted you to recognize that the altitude of the sun is up here, right? You would go to your nearest horizon, which is your southern horizon, and the angle would be, that's the altitude of the sun. It's the degrees up from the closest horizon. So not 180, Jenna, but if this is 80 degrees, and Ian eventually did get there, we have to subtract from 90 to get theta. Do you see what I mean? The trick to this problem was recognizing that they didn't simply give you the angle in the formula, but that they made you do a little bit of astronomy, okay? So theta is 90 degrees minus 80 degrees, 10 degrees. And now we just plug it in and we get the answer and we're done. The circumference is 360 degrees over 10 degrees times 1,000 kilometers. Honestly, you don't even need a calculator for that. 360 divided by 10. What's that?
36.
36 times 1,000 gives you I guess punch on your
36,000.
Sorry?
36,000.
Units?
Sorry, I was muted. Kilometers.
Good. And that's our final answer. Kim, would you like to read us a question? Last time your microphone was a little quiet, so I took. How you doing today? Can you hear me?
I'm fine. Yep.
Oh, you sound loud and clear today.
I changed the settings in Zoom. That's what I had to do.
Great, great. It sounds much clearer now. Does anyone need a second, or can I erase this, Jazz? All right, I'm erasing. Two down, three to go, and they're going to be quick. If anything,
Okay.
I'm slowing us down today. I keep feeling the need to teach you guys stuff. I don't know what's wrong with me. Okay, chapter 3, number 52. What do you think, Kim? Read me the title.
Yep. Eris orbit. The dwarf planet Eris orbits the sun every 557 years. What is the average distance? And in parentheses, it says semi-major axis from the sun.
Do you guys know what Eris is? Who knows what Eris is?
Sounds familiar, but I don't quite remember. Is it something in the Kuiper Belt?
Yes. It is a dwarf planet in the Kuiper Belt. What is it famous for? It's famous for being the object that got Pluto kicked out of the solar system. We discovered Eris was bigger than Pluto, and we couldn't let Eris into the solar system because then we were going to have to let all the other Kuiper Belt objects into the solar system as planets. So instead, we demoted Pluto, which of course pissed a lot of people off because they felt like they were losing a planet. In fact, they gained an object. Now, unfortunately, Eris, the dwarf planet, we don't have a good picture of it. This is our best picture to date of Eris. It's so far from the sun that, it's so far from the sun that even with powerful telescopes, it only appears as like a bright spot. And do you see the secondary spot? Eris actually has a moon called Dysnomia. That hasn't stopped artists from trying to imagine what Eris would look like. We imagine it would probably look kind of like Pluto, like an overgrown ice ball with frozen nitrogen on it. So here's a weed-smoking artist illustration of what the moon Eris might look like. This is a pretty good one, actually. And of course, they're basing it off of what we know Pluto to look like. Anyways, what should I do, class? This is a real easy problem. We know it has a 557-year orbit. How, oh gosh, could I ever find its average distance / semi-major axis? Let's pretend this is a test question. You'll have a little formula sheet with all the formulas. You got to pick the right one. What's the formula that we want here?
You're going to need the harmonic formula.
Booyah. And how does that go? Am I talking to Paul G there?
Yep.
Paul G, how's that go?
P squared equals A cubed.
Okay. But I suppose, Paul, this is probably obvious to you. It's obvious to me. Which letter are we solving for here?
We're going to look for a P.
Ooh. Are we looking
No.
for P? What does P represent?
The perihelion.
No. Perry for
No,
perihelion.
Perry's for perihelion. Yep.
It's okay, Paul. Keep going. What else begins with P? Pinochle, peanut butter sandwich, Pinocchio. None of those things have anything to do with a planet, though. So,
Period.
Period.
oh, right, the period. Okay. And then what does A represent?
Average distance in AU.
Which is what we want. So we should rearrange the formula. Let's start by rating A cubed is equal to P squared. How do I get rid of the A? We want to find A. That's what the job is. How do I get rid of that cube?
We find the cube root.
That's right. We cube root both sides. So A will equal the cubed root of P squared. I want you guys to notice my clean, yeah, Ryan. I want you to notice my clean math styles. I always solve for the variable I want, and then I plug in the numbers. It's vulgar to plug in the numbers and then try to manipulate an equation. Never do that. Okay, what is the period in this case?
557 years.
Good. I wanted to make sure you guys recognize that. Nice, Kim. So we will do the cube root of 557 years squared. You guys ready to try this one out? This is different than the sample problem we did in class today. Let's start with 557. And now find your square key, which is right up there, and hit it. Now we're going to get the cube root key, which is above the plus minus here. We have to hit shift and then negative key. Okay, Nori, today we talked about sig figs. How many sig figs do we have going into the calculation?
3.
So how many do I get to keep here?
3.
So what should I round my answer to?
67.7.
Good. And last part, what are the units?
You want the average distance.
This is kind of a magical formula, so you have to know what the units come out as.
Would
Sure.
it be years?
No, this is a distance. We can't measure distances in years.
AU?
That's right. This formula always pumps out the semi-major axis in AU. And that's it.
Isn't it? It's 67.7, right?
Oh, sorry. Wow.
57?
That was
Wait,
last
oh
week.
yeah.
Sorry.
Did I say
Me, or was that
57
you?
or 67?
I think that was last night's whiskey talking for me. All right. So, did they ask us to do anything else? Who was our reader there? Kim?
Yep. What is, oh, no, how does it, how does this average distance compare to that of Pluto?
In the sample problem today, I gave you the distance to Pluto. What was that? So 67.
Of 39.5?
Right. So what do you get if you divide those two? Huh?
Hang on one second.
Oh.
1.75?
Let's say about 1.8 times farther than Pluto. So Eris is actually really out there in terms of our solar system. In fact, I bet if we go to that Wikipedia page, I bet they're going to show us. I bet they're going to show us a model of its orbit compared to Pluto, because that seems like a thing that people would find interesting. Come on, internet. Eris, the dwarf planet, Wikipedia, and let's just scroll through the pictures real fast here. Yeah, sure enough. So let's look at the picture. Oh, wow. I never realized that. Look how inclined to the ecliptic plane Eris is. That's wild. So look, here's Pluto's orbit, which is already kind of squishy. Look how squishy Eris's orbit is. It actually comes almost to the orbit of Neptune at its closest approach, and then it goes out well past, almost 2 times farther than Pluto. And what I did not know until right now, I just learned something. I never realized that its orbit was that inclined to the solar system, if that's what I'm seeing there. Its inclination is 44 degrees. That's wild. That means it doesn't really orbit in the disk of our solar system. That's very interesting. Okay, let's knock this one off and let's move on. Next question is 53. Jenna, you want to read that for us?
Oh, can you not erase this for a second? I still need to write some stuff down.
Sorry.
Thank you.
Yeah, I need to see the bottom also.
Sorry, guys. Let me know when you're done.
I'm done. Thank you. I don't know if everyone else is.
I'm good too.
Okay, here we go. Jenna, what do we got for 53?
Okay. It says new planet orbit. A newly discovered planet orbits a distant star with the same mass as the sun at an average distance of 112 million kilometers.
How would I write
Its
that
orbital.
down? Sorry to interrupt, but if I wanted to write down 112 million kilometers, how would you write that down, Jenna?
1.12 times 10 to the 6th.
Wrong. You did something wrong. What was it? I was worried that you were going to say that, Jenna. That's why we're having that chat.
Is it 1.1? Like for sig figs, not.
You're overthinking this, Jenna. I know what you're trying to do. You're thinking, oh man, he wants me to put it into scientific notation. That means I'm going to have to put 1 followed by a decimal point. What if you thought about it differently, Jenna? What is a million equal to in scientific notation?
I see what you're saying. Put 10 instead of 1.
No, it's 112 million kilometers. There's a simple way to write this. Does anyone understand what I'm driving at, or am I confusing you guys?
I do.
Oh, Ian, what do I want to write down?
At least I think I do. So it's 6 zeros is a million. So you would do 112 times 10 to the 6th, right?
Yeah. The idea is you don't need to put a decimal point there, Jenna. You just tack on 10 to the 6 instead of a million. If you wanted to do it your way, Jenna, you'd have to move the decimal place 2 more times, and you would have had to do 1.12 times 10 to the 8. But that's so less cool than 112 times 10 to the 6, right? That's all. That's my only point. I'm wondering, suppose I wasn't here to guide you through this problem, would you have done that right? These are the things we have to worry about. Okay, keep going.
I have a quick question before she starts reading. I'm
Yeah.
sorry. If you did it the way she said to do it, would it come out any different?
Nope. As long as you managed it correctly. If she had wrote down 1.112 times 10 to the 8 kilometers, this whole problem would be exactly the same because this number is equal to that number. The only thing is for her to go in her mind, because they wrote it in the book as 112 with the word million, she would first have to do this in her head and then move the decimal place 2 more places. So she has to think harder. That's why this is, I just wanted to show you guys that when you see the word million, you just plop down 10 to the 6. That was the moral of the story. Okay, keep going.
Okay. Its orbital eccentricity is 0.3. Find the planet's orbital period and its nearest and farthest orbital distances from its stars.
What do we call that again? The nearest and farthest distances to the star. We call that, I can't remember the words. I'm forgetting them. If only one of my students could help me. I wouldn't be so forgetful. The closest approach to the star, the farthest distance from the star. What? I know there's a word for that.
Perihelion and aphelion.
Oh, right. Okay. So find the perihelion and the aphelion distances. By the way, when it's not the sun, we actually call it periastron and aphastron, but I'm not through there. Okay, what do? I'm confused. How do I solve this problem, Jenna?
Wow.
This is some tough stuff here. Just give me your first thoughts. You need an equation.
Yes.
This is the average distance between the planet and the star, right? If only I had a formula that would give me the period based on the average distance. That would be awesome.
For the peri, it would be A times 1 minus E in parentheses.
Very good. That's the formula we're going to need for the perihelion. But
And-
let's keep, was that Kim? Let's keep our powder dry. Kim, let's keep that in our back pockets. And what's the aphelion equation?
A times 1 plus E.
And Kim, the reason why I don't want to tackle that just yet, I can't explain it, but I will in a moment.
Okay.
I want to do something first, but I can't spoil the surprise. Okay, but that's good for perihelion and aphelion, Kim. What about for the period?
Period. Isn't that hang on. The harmonic law, P squared equals A cubed.
Hell yeah. Always. P squared equals A cubed. Okay, Kim, so if you were solving this problem without my help, what would you do next?
The one sorry.
That's okay. The dog's got an idea. We should ask him what's up.
Stop. Stop, guys. 112 times 10 to the 6 squared.
Whoa, hold on.
Right?
It's P squared equals A cubed. The first thing I need you to do is to identify which letter this number corresponds to.
Okay. Is that P? 112 times 10 to the 6?
No, because
it's the
P is the period.
Okay, sorry. So E, it would be 0.03 squared equals.
E is the eccentricity, Kim.
Oh, jeez.
P squared equals A cubed does not refer to the eccentricity.
Yeah.
That's okay. We got to do this. We got to smash our heads against the wall a little bit here.
Here.
Why don't you just go back to your notes where I defined P squared equals A cubed and see what it says underneath them.
One's year, one's AU.
Okay,
P
what else did I
squared
say?
year equals period of the planet in years and average distance of the sun to the planet in AU.
Okay. So which letter did they give us then, Kim?
They gave us the distance.
Which is what letter?
A.
Which is A. That's what I wanted to say. So can I just plug in 112 million then for A?
Yeah.
No, Kim, I can't.
Well,
there's something wrong.
The eccentricity. Oh.
No, the eccentricity's got nothing to do with it. Let's just focus on the 112 million kilometers. I can't take 112 million and punch it in for A. I can't do it. Something's wrong.
It's not an AU?
Correct, Jenna. Remember, I put that underneath. It has to be an AU. Kim, that sounds like a U job. Could you help me convert this to AUs using your powerful dimensional analysis skills?
It's been a while.
I think I found it.
Okay. Okay.
Sorry, if he wants to do it too, I wasn't sure.
No, that's fine. No, that's fine. I was looking for it.
Because I found that 1 AU is equal to 150 times 10 to the 6 kilometers.
That sounds helpful. That's our conversion factor from kilometers to AU. We're definitely going to need that. Good job. So I hope you guys can understand what I'm trying to do here. I know that you want to get the homework done, and I want to get it done too, so I can take a big boy nap. Okay, but what I want to do is I want you to kind of try to force your way through the problem and let me help you when you need a little push. The more you can do this independently, the better you'll be prepared for the test. So just try it. What I need you guys to convert kilometers to AU. Can you do that for me? Tell me what to write.
So we'll take the original A equals 112 times 10 to the 6 kilometers. Then we multiply it by a division bar.
Yep.
We put kilometers on the bottom, and we're going to say 150 times 10 to the 6.
Oh, no numbers
sorry.
until both your units are in place. You did say kilometers on the bottom. I didn't hear you say anything else on top.
And AU on top.
Okay. Did you glitch out or something? Is that what it was? I don't know. Anyways.
Maybe. And then we're going to put 1 as the unit for AU on top, and 150 times 10 to the 6th kilometers on the bottom.
Beautiful. Punch them up. Geez, guys, I'm going to grow old and die waiting for you to punch this into your calculator here.
I got 0.747 AU.
Okay. I like your sig figs. You know what we're going to do? We're going to have some fun. Ian, you did okay with the 3 sig figs, but let's just round it to 0.75 for kicks. Okay. Sometimes we can break the rules if we feel like it. And that's AU, right?
Yes.
So now we have our A converted into astronomical units. Now, Kim, we can deploy P squared equals A cubed. All right. So if I were to write P is equal to, what should be on the other side of that formula?
The square root of A cubed.
Very good. The square root of A cubed. So we want the square root of 0.75 AU cubed. Why don't you guys see if you can do that without my help? The last 2 times I showed you how to punch it. Now demonstrate that you can do it without my help.
I got 0.65.
Units?
0.65 AU.
Not AU.
Or no, years, because it's
yeah. The P squared equals A cubed kind of magically transforms the units. Yeah. Oh, by the way, it turns out that Kepler invented the astronomical unit. Because he figured out P squared equals A cubed, he could only figure out how far away the planets were in terms of Earth-Sun distances. But he didn't actually know what an AU was, so he didn't really know how far away Saturn was, which is kind of funny. He could tell you it was 10 times farther from Earth. 10 times farther than the Earth-Sun distance, but that's all he could do.
I tried to punch it in and it didn't come out right.
Okay, then that's good. Let's do it now together. 0.75. Okay, first we're going to cube it. We're going to shift and hit the backspace key to cube. Now we're going to square root it, shift, and the square root key is right there.
Okay.
Good job. Okay. That's the period. Now we've got to get the perihelion and aphelion. The reason, Kim, that I didn't want you to do this part first is, Kim, you could have put 112 million kilometers in for A there, but I would consider that vulgar. It's so much more elegant to work in astronomical units than in kilometers. The numbers just look better, okay? So let's do that to get, I need to erase a little bit, guys, if that's okay. Maybe I'll erase up top, okay? The perihelion is A times 1 minus E, so we'll put in 0.75 AU times 1 minus 0.3. Why don't you guys punch it in, see if you can get the right answer without me first. Then I'll show you how if you stumble. Whoever gets it, just shout it out. Don't be shy.
0.525.
That's a bit ambitious, sig figs wise.
0.53
Units?
AU.
Beautiful.
Yeah.
Yeah, that's good. Does you have AU on this side? Okay, I like to use a capital U. For the Aphelion, it's quite similar. 0.75 AU times 1 plus the eccentricity. I'm feeling the burn, guys. And I ain't talking Bernie Sanders.
I got 0.98
Units?
AU.
Nice. One more to go. We're making good time here, I think. I think we are. Oh my, it's almost 3. Well, I was hoping to make better time than that, but better time than last week anyways. Can I erase? I'm erasing. Hey, Ryan, I haven't heard from you today. You've been part of the party. How do you feel about reading the last problem for us?
All right.
Okay.
Hold on.
Chapter 354.
Halley orbit.
Did you say Halley's orbit?
Yeah, I meant to say Halley. Sorry.
Is it Halley's comet or is it Halley's comet? Halley's comet.
Halley's orbit. Right? Yeah, it is Halley.
Okay.
Okay. Anyway, Halley's comet orbits the sun every 76 years and has an orbital eccentricity of 0.97. Find its average distance from the sun, semi-major axis, and find its perihelion and aphelion distances.
Okay, that shouldn't be too hard. Did I remember correctly that they gave us 76.0 years, Ryan?
Yes, it did. Sorry, I forgot to say 0.0.
That's for sig fig reasons. That means it's good to 3 sig figs. Okay, Ryan, what do you think we should do? How could I possibly get the semi-major axis of Halley's comet orbit?
Is that the
Yes.
harmonic law, which would be p squared equals a to A cubed.
Very good. And which letter am I trying to get or solve for here?
That would be A.
Okay, so let's write it the other way. Let's write A equals, we'll do the cubed root of P squared. I believe we have the period, Brian, correct?
Yes, that would be 76.0 years.
Okay. This will be a good test, Nori, to see if you can get it this time without my help. See if you remember how to do that, right? If not, I'll show you again. Punch him up. Let's hear what Nori gets.
We were cubing the root, right?
Oh, wow, wow, thank you. I was just testing you, Nori, to see if you were paying attention, and congratulations, you passed the test, okay? Wow. That was some amateur hour stuff right there.
Um, 17.9.
Nice. Now give me some units.
AU.
Very good. Oh, wait, yes, very good. I had to think about it for a second.
Would we round it up to 18 or would we not?
Well, this is why I was bugging Ryan about the 0.0. 76.0 is different than 76. 76 means I know the period to the nearest year. 76.0 means I know the period to the nearest tenth of a year. Since there are 3 sig figs going into my computation, I am allowed, if I want to keep 3 sig figs coming out. On the other hand, yeah, 18 AU would have been a little bit cleaner and nicer to look at, but we're, since I made a big deal about the precision, I'm keeping 3 sig figs, whatever. Okay, now let's get the perihelion distance. Perihelion is A times 1 minus E. The A is 17.9 AU times 1 minus 0.97. Punch him up. Oh.
Got 1.43.
I'm sorry, could you say that again, Ian?
I got 1.43, and it would be.
That doesn't sound familiar. Did anyone get something else?
I got 0.537.
Okay, I must have done something really
Yeah,
wrong.
I got 0.537 too.
Okay. So 0. Oh, can you keep 3 sig figs?
Yeah.
No.
But you would take away the 7, so it would be 0.534. 0.54.
No. You guys are missing something. You cannot keep 3 sig figs anymore. Why not? Someone tell me why 3 sig figs is no longer valid.
Is it because the 0.97 doesn't have an actual number in front of it? It's just 0?
No, that's not the right way to say. It is because of the 0.97, but I didn't like the way you said that. The eccentricity of 97%, this is a measurement, and this measurement has precision. Oh, I see. Now I understand the way you're saying it. Yes, this number only has 2
sig figs.
Yeah, that 0 doesn't count. So this pollutes our answer, and we now have to round it to what?
0.54.
And the units are?
AU.
Good. In fact, if I had to guess, I bet we know the eccentricity of Halley's Comet a lot better than that, and I bet it's the book that rounded it, which is okay, but I'm just trying to demonstrate that eccentricity is a measurement. And for dramatic demonstration, here on the Wikipedia page, notice that we actually know the eccentricity of Halley's Comet to 1, 2, 3, 4, 5 sig figs. Some crazy nut has measured it to 0.96714. I sure like to read that research paper when I'm trying to fall asleep at night. Okay, here we go. Let's get the aphelion and then we're done. Aphelion is A times 1 plus E. That's 17.9 AU times 1 plus 0.97.
Yeah, I just realized that I used the wrong eccentricity. That's why.
Oh, was that? I actually meant to follow up with you, Ian, and see if you fixed your mistake.
Yeah, I did. I put, for some reason, 0.92 instead of 0.97.
7s and 2s get confused. Ooh.
For this one, I got 35 for the F and
give me the units.
AU.
Very good. Which is almost out to the orbit of Pluto. As I mentioned today about comets, comets oftentimes come interior to the orbit of the sun. That's when they get their tail. And then they go outside the orbit of Neptune, where they freeze back into ice balls. Okay, guys, you've done it again. You've lost another 3 hours of your life learning astronomy with me. Please turn in those
Wait,
homework.
what was the last answer? I'm sorry.
Oh, sure. 35 AU.
Okay.
Okay. Our work is done for the week. Like I said, one last note. I probably won't go to upstate New York next week, but if I do, I'll still try to have live class. It just might be me sitting in a weird room. I don't know. I kind of like having my props around, so I don't know if I'm actually going to go, but I'll do something. And I'll be there at noon on Monday. Please turn in your labs and homeworks by Saturday, okay? So Ian, get that other one done, okay? Get that lab done from this week. Same with you, Nori, and everyone else. Okay, any last?
I have a question.
Sure.
I don't know if it's just the way Blackboard grades it or if it's not, but my grades aren't good, and I submitted like everything. Like it says like 45 out of 75.
Okay, hold on.
Which doesn't make any sense.
Let me explain what's going on there. Other students might have this issue. First of all, Nori, I'm glad you brought this up because sometimes you guys think that you're submitting labs and then it'll get hung up as an attempt in progress. If it's an attempt in progress, I don't think I can easily look at it. There were a couple of people, and you might have been one, Nori, who just totally went off and did not give me what I was looking for. Now, it was only a few students, but did you type up your first homeworks? Was that you?
No, I hand wrote everything. I have it like this. I don't know if you remember, but
hold on, let me see. Hold it up again.
That's like usually how my homework looks.
That's regardless. Great. Okay. Let me explain what's going on there. There's another thing that I want to talk to you guys about. Blackboard sometimes tries to compute like the total grade, but it's not using my algorithm. So when you look at your grade in the grade center, and let's just look at yours together, Nori, if that's okay.
Yeah, that's fine.
What's your last name again?
Mourad, M-O-U-R-A-D. Right there.
There you are. So the things that you guys should just look is like, all right, so you're 3 up. Don't look at that 45. That 45 is just a dumb total. What I can see here is that Nori, you've turned in and have a perfect on lab 1. You've turned in and have a perfect on lab 2. And for homeworks, I really hate this freaking system. It's so awful. So Nori, I got homework 1 from you. This is why your grade might not be so good. Oh, I see what happened. Nori, you were the person. You turned in your homework 2 into homework 3 slot. You were that person. I knew I remembered your name for some reason. I was so mad at you. I was like, why?
I'm sorry.
Now look, I'm willing to go. You did do that work, right? I
Yeah.
cannot give you credit if you do crazy shit like that. My whole life will fall apart. If students just start
I'm sorry.
submitting homework 2 in whatever slot they want, I will lose my mind. So you currently have a 0. I was waiting for you to come talk to me. I will put
Okay.
your grade back in.
Okay.
You need to, oh my gosh. I don't know if I
I'm
can.
so sorry. I can't unsubmit it though. I can't do that.
No, that's
it won't
okay,
let me
'cause
submit it again either.
You have infinite do you have the photo with you?
Of my work?
Yes.
Yeah.
I'll tell you what, let me end the thing and then let me let everyone go who doesn't feel like listening to this. Oh, wait, hold on. Wait, before, Kim, are you Kim Neville? This is the shit that I'm really scared about, Kim. You're in big trouble, Kim. You didn't actually get graded for homework 1 because it got hung up as an attempt in progress. And look, I saw it with your labs too. Your labs are hung up as, oh my God, all of your, yeah, I got you lab 1, but Kim, somehow you're closing out your browser before you finish your attempt in progress. And sometimes I can't look at these. This is what scares me because you guys think that you've submitted your work, but I don't get it in my needs grading center. So Kim, can you try to go in and fix that? Oh, you're muted, Kim, sorry. Are you listening to me?
Yeah, no, yeah, I'm listening. I'm said I was going in right now to look at it.
You've got to, and I'm talking not just to Kim here, but I'm talking to everyone else. There are too many of you for me to try to track you down because I usually don't even go into the full grade center. I just go to needs grading. Now, I don't know if I can look at this. Sometimes I can and sometimes I can't, but I don't want that. I want you guys to show me I want it to be a proper submission. Now I can open this. Nori, here's what we're going to do.
Hang on, let me
Mhm.
get in there.
Nori, do you have your homework 2?
Yeah.
Ready to go right now? I'm going to
Mhm.
temporarily make this available so you can submit it. But you will
Okay.
never do that again, right, Nori?
Oh, I hope not.
I hope not too, because I will give you a 0 despite.
I'm sorry. I didn't
Despite
mean
me having
to.
good feelings about you, I will give you a 0 if you ever do that again, all right? So
Thank you for this though. Like I appreciate it a lot.
sure. All right, so submit that right now so I can deactivate that again. And Kim,
Did
I
you
don't know
put
if
it
I need
in
to do
homework
that for
too?
you. You might be able to go and look at your submission in progress and then finish submitting it. Can you do that?
No, because when I go into Blackboard in that section, it's only going to like lab 3.
All right, let's temporarily make this all available. Oh, this is so ugly. See, this is the kind of stuff that I don't like getting sucked into because it's just ugly. Okay, right now, everything is available. Can you,
Okay.
I'm going to leave this up for like 1 hour. Can you guys
Okay.
please take care of all your stuff?
Did you open up homework 2?
I did. I think, yes. Do you see it?
No.
Is your Blackboard open?
I'll log in again. Maybe that's why.
All right. I'm actually going to end the recording here. I'm going to stay on with you guys to fix this, but people watching later probably aren't going to be interested in this. So I'll see the rest of you on Monday.